Hello everyone, my name is Zheng. My topic today is about the Dexterous finger force estimation using motor unit discharge information. 30 million people are in need of prosthetic and orthotic devices all over the world. In order to take full use of many advanced robotic hands with the ability to control individual fingers, a reliable neural machine interface needs to be developed. Neural signals can be obtained at different levels, such as the central and peripheral nerve systems, and also the muscles. Among these signals, the surface EMG signals show promising application prospects due to its non-invasive nature and property of low cost and high signal-to-noise ratio. In order to control robots in a continuous manner, proportional control was developed. Typically, global features such as EMG amplitude were extracted continuously and used as the control input of a specific degree of freedom. However, due to some factors that can substantially affect the EMG recordings, such as the background noise and motion artifacts, the control performance can decrease significantly. In order to address these issues, we have demonstrated that the motor unit discharge information decomposed from the EMG signals can be a more robust measurement of the muscle excitation level compared with the global EMG features. This method regards the composite firing rate of a motor unit pole as a good estimation of neural drive signals into the motor unit pole. However, in our previous study, only extension of one finger was involved, and the EMG signals were captured from the superficial EDC muscle, and it is not clear whether the motor unit discharge information decomposed from the deeper finger flexor muscles can be accurate enough to predict finger flexion force. In addition, it needs to be investigated how to predict dexterous finger force when both flexion and extension are involved. During our experiment, we recorded high-density EMG signals from the finger flexors and finger extensors and the isometric force of individual fingers. Due to the enslaving effect, we considered the ring and pinky fingers as one finger and always requested the subjects to extend or flex the two fingers concurrently. The motion tasks required the subjects to follow a repeated trapezoid trajectory. Subjects performed two types of trials. The first type was single finger trial. Subjects flexed or extended one specific finger in a trial. The second type was multi-finger trial, in which 2 or 3 fingers flexed and extended in sequence within a trial. Force estimation based on neural drive signals mainly involves 3 steps, including the acquisition of motor unit separation vectors, motor unit pole refinement, and force estimation. In the first step, we used the single finger trials to get the motor unit separation vectors for the flexion and extension of individual fingers through the FastAssay algorithm. These separation vectors can be applied to new EMG data to extract discharge information of the corresponding motor units. Here we illustrate the force data of a representative single finger trial with index extension. This figure shows the spike trains of the decomposed motor units, which were put into the motor unit pool for the index extension. And after repeating the EMG decomposition across all single finger trials, we obtained the motor unit separation vectors of 6 motor unit pools for the flexion and extension of 3 fingers. Due to the co-contraction of other fingers in the single finger trial, a specific motor unit pool at this stage might actually contain the motor units from other fingers. Therefore, we performed a refinement procedure using the multi-finger trials in the second step. Here we divided the multi-finger trials into the training and the testing sets and performed a 4-fold cross-validation because the force estimation performance was also calculated using the multi-finger trials. And in this step, we used the multi-finger trials from the training set. Since the motor unit firing rate is modulated by the contraction force, The firing rate of a specific motor unit correlates with the force of the finger innervated by the motor unit. And based on this, we first obtain the firing rate of individual motor units for a specific finger using the corresponding separation vectors. For example, the index extension in this schematic diagram. Then we perform the correlation analysis between the firing rate of each motor unit and the force of 3 fingers, and removed the motor units with firing rates that had a stronger correlation with other fingers, that is middle and ring pinky fingers, in this schematic diagram. The motor units with red spectrum is illustrated here from the representative single finger trial were removed from the index extension motor unit pool. In the third step, we estimate the force using the multi-finger trials from the testing set. First, we calculate the neural drive signals for the flexion and extension of individual fingers using the refined motor unit pools. Then we performed a multiple linear regression analysis between the force data and the neural drive signals of flexion and extension for individual fingers. And the resultant R-square and the root mean square error were used to evaluate the force estimation performance. In order to compare the performance with the conventional method, the EMG amplitude-based method was used as the control. The overall procedure of the EMG amplitude method was similar to the neural drive method. First, using the EMG data from the single finger trial, the 60 most active channels were selected for the flexion and extension of 3 fingers, that resulting in 6 EMG channel groups. In order to minimize the issue of crosstalk, a channel group refinement procedure was also performed using the multi-finger trials in the training set. Here we analyzed the correlation between EMG amplitude of individual channels and the force data of 3 fingers. Then we used the multi-finger trials from the testing set for force estimation. Specifically, we calculated the overall EMG amplitude for individual channel groups. Then a multiple linear regression analysis between the force data and the 2 EMG amplitude signals was performed for individual fingers. Here we illustrate the spectrums of individual motor units for the extension and flexion of index finger from a representative multi-finger trial. The thick curves represent the normalized neural drive signals. Here we show the force prediction results of individual fingers using both the neural drive method and the EMG amplitude method. And the neural drive method can predict the force accurately in most cases. On the contrary, the predict force using the EMG amplitude method had both over and underestimated issues, especially for the index finger. The average R-square value and RMC are shown in Table 1 for individual child subjects. The results show that for all subjects, the neural drive method showed better performance compared with the EMG amplitude method, manifested as a larger R-square and a smaller RMSE. The major result of this study is that the neural drive method can predict the isometric finger force accurately when the fingers performed dexterous flexion and extension. And compared with the EMG amplitude method, the overestimation and underestimation was much smaller using the neural drive method. Therefore, the neural drive method can potentially provide a robust neural-machine interface for continuous control of assistive or rehabilitative devices with high dexterity. One limitation of the current study was that only a linear regression model was used to establish the relation between the force and the neural drive of extension and flexion. However, since the relation might actually be nonlinear, more complex models will be tested to evaluate whether the force prediction performance can be further improved. In addition, more subjects will be recruited and more metrics will be used to verify the performance of the neural drive method in predicting dexterous finger force. Thank you.